Hello, everyone. This is Mrs. Hilt with your lecture on specific heat. Please follow along with either your own notes or the lecture slides I posted on Google Classroom where you can fill in the blanks as we go along. All right, so we are starting off with a little review. I want you guys to identify the term that is supposed to be in the blank. Go ahead. All right, let's see how you guys did. First, temperature, average kinetic energy, or energy of motion, or average speed of all of the particles in a material. Thermal energy, total kinetic energy of all of the particles in the material. And heat is the energy transferred between two objects of different temperatures. So we brought this up again because this lecture we are going to talk about how heat is transferred between substances and actually be able to calculate what that heat is. And to do so, we will need to talk about temperature and temperature changes. All right, so the objective for this lesson, or objectives, are to define and state the units for specific heat, compare substances based on their specific heat, explain how mass, specific heat, and temperature affect energy, and how to calculate the amount of energy it takes to raise 1 gram of a substance up 1 degree Celsius. So we're doing a lot in this lecture. All right, so the first thing that we're going to talk about, I need you guys to actually move around. So whatever room that you are sitting in, I want you guys to find two objects that are different materials, such as a book or a metal bed frame, or maybe a metal like leg of a chair or leg of a desk, anything like that, or just any two materials or any two items that are different materials. Pause the video and answer these questions. When you're ready for more, press play. All right, so now that you guys have answered these, we are going to watch a short clip.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. Oh, that's warmer. Yeah, way warmer.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that, and I'm not a scientist.
Make a prediction for me.
I still think that's cool though.
Would you bet me money?
I don't because I don't have any cash, so yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. All right, well, now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature.
All right, so the two objects in this video, the hard drive and the book, they're actually the same temperature, even though everybody was saying that the hard drive clearly felt like it was colder and it would definitely be a lower, or they all thought it would definitely be a lower temperature. So I'm curious if you guys said that as well, if the metal object that you chose, whatever it is, felt colder than the other object. And even though I'm not with you right now and we can't like prove this with the infrared thermometer that he had in the video, but if your objects were sitting in the same room, I can almost guarantee that they are the same temperature unless there's some outstanding factor to cause them to change temperature, such as something was sitting in the sun that was coming through your window, or something was sitting right next to the air conditioning that was blowing out, or something like that. So as long as there's no outside factors, everything in the same room, in the same area, should all be the same temperature. Okay? So just because something feels colder does not mean that it actually is. And the reason why is because the material that substances are made up of, when you touch them, they feel a little bit different. But why? Like, what causes this? Like, why does something that feels the same temperature, like a metal hard drive versus a book, why does the metal hard drive feel colder? And you guys probably have experienced this. And it's all about the amount of energy required to change the temperature of that substance or that material. So, different substances require different amounts of energy to change temperature. So, the book, it requires a ton of energy, or any type of paper material, especially like cardboard, takes a lot of energy to change temperature. But something like metal, it doesn't require a lot of energy to change temperature. It will heat up and cool down very, very quickly. That's why if you ever put aluminum foil in the oven, you can generally touch the aluminum foil pretty quickly after pulling something out of the oven, because it changes its temperature very rapidly. It does not take a lot, or it requires very little energy to get back to the normal temperature. Right? And things that are considered to be poor thermal conductors, it takes a lot of energy to change temperature, like the book. And then things that are good thermal conductors, they take very little energy to change temperature. And how we feel this, like when it actually comes to the touch, is that the hard drive, the metal, it's taking energy from people's hands, or whatever metal that you were touching. It's taking energy from your hand much faster than the non-metal item. All right, and I have another experiment. This is one that I did to show how heat is being extracted by different materials at different rates.
Okay, so we have 4 different materials. We have a wood cutting board, a brownie pan, an an iPad stand, and my granite countertops. I'm going to put an ice cube on each and see what happens. Thank you. Alright, let's zoom in on these. So, first, cutting board, not much action. The pan, let's move that around a little bit. Alright, got some water. Countertop, a little bit of water. And the iPad stand, we have a little puddle already starting. Alright.
Okay, so we'll come back to that in a little bit. But right from the get-go, you can see that the ice cubes are melting at different rates. And I can promise you that all the ice cubes were about the same size. I can't guarantee they're exactly, but they're all very close. And all of them they're exposed to all the same things. And all of the items in here, the countertop, cutting board, pan, iPad stand, they were all in the same room. So they should be all the same temperature. All right, and what we are all looking at is specific heat. So specific heat is the measure of how much energy it takes to raise the temperature of a substance. Okay? And the more detailed definition of specific heat is the amount of energy in joules, so we're still using joules for energy, needed to raise the temperature of 1 gram of a substance up 1 degree Celsius. Okay, and I know this is only talking about increasing temperatures, but you can also calculate it for decreasing temperatures. It would just be negative. Okay, and different items or different materials have different specific heats. And if you look at the table at the bottom, you can see that things like iron, so a metal, has a very low specific heat, versus something like wood, which is a little bit higher specific heat, and then all the way to water, which is much higher than all of those. So what that tells us is that it is much easier to increase the temperature of a material made up of iron versus wood. It takes a lot more energy to heat up wood, or to heat up energy, than it would iron. So let's have an example for you guys. If you were to stir some boiling water, maybe you're making soup, which tool would you want to use? A metal spoon or a wooden spoon? Pause the video, make your selection. All right, so I hope you guys picked the wooden spoon. And generally, big spoons in the kitchen, or at least my kitchen, they're either wood, or if there is metal part of them, they have some type of rubber over it so that your hand doesn't get hot when you stick the metal spoon in hot substances. But metal spoon would get way too fast because hot way too fast because of its low specific heat. It does not take much energy to increase that substance's temperature versus the wood. It takes a lot of energy to increase the temperature of wood. Therefore, it's better in hot substances. All right, let's go back to the video and see how those ice cubes are doing a little bit further down the line.
Okay, so we have.
Oops. That was supposed to cut right to it. I apologize. Okay, so this is, all right, so this is after about.
All right, now 1 minute has passed. Let's check on our ice cubes again. Here is our cutting board. A little bit of dampness under that. We have, my hand looks enormous doing this. Okay, got a little puddle there, but most of the ice cube is still left. Countertop, fairly similar to the pan. I would say that this ice cube is still a little more frozen than water. And the iPad stand, we almost have a fully melted ice cube.
All right, so that was only after a minute. And at the top, as you guys can see, I outlined the different substances that each of these were made up of. So the only thing that I personally am unsure about is that non-stick surface on the aluminum pan. But we'll get back to that later. All right, so based on what you guys just saw, I want you guys to rank the different materials based on what you think their specific heat would be. Okay, so 1 being the lowest specific heat, meaning it requires the least amount of energy to increase temperature. 4 being the greatest specific heat, meaning that this substance requires the most amount of energy to increase its temperature. All right, pause the video and rank the substances. All right, so when I ranked them, this is what I got. And the little C that you see next to each of these is the specific heat value. And we'll get into what the units are with that very soon. But as you can see, the one that was melting the fastest, the iPad stand, which is an alloy, it's made up of multiple metals, has the lowest specific heat. Therefore, it takes the least amount of energy to change the temperature. That's why the ice cube is melting the fastest. Whereas the wood cutting board has the highest specific heat, and that's why it's taking the longest to melt the ice cube. Now, based on my video, the granite countertops look like it was not melting as fast as the aluminum pan. And when I looked up their specific heats, they're actually very close to each other. So being only 0.11 of a difference, that's extremely close. And the nonstick surface of the pan very well could have had an impact as to why it was melting a little bit quicker than the countertops. And I could not find the specific heat of an actual pan. That's something that we could calculate if we did a lab, though. All right, so now how you guys actually go about calculating specific heat is with this equation at the bottom. Q is equal to mc delta T. So it involves the mass, the specific heat, that's the C, and a change in temperature. All right, and Q, of course, is the heat, and that will be measured in joules. As you guys can see, the units are listed below the equation at the bottom. Mass is in grams, so it's consistent with for what we've been working with. And temperature is going to be in degrees Celsius. And how we find the delta T, or the change in temp, is just by taking the final minus initial. All right, and then the values for C, you will either always be given this or it's what you're solving for. So if you are ever not given C, you must solve for it. All right, and let's practice that calculating with that equation. So you could do this comparison just based on the quantities that are there, but I want you guys to get practice with the calculation of this as well. All right, so make sure that you guys reference, oops. Okay, let's get some practice identifying which one has more energy. So you can definitely make the comparison or identify which one would take more energy just based on what you see here. But I would like you guys to get some practice with the calculations or the equation on this slide. So Q equals mc delta T. Use that for all of these. And if you ever need to find the C, in the second one it is given to you, but the specific heat for water, just refer back to this slide. All right, pause the video, try plugging in some numbers. And if you need some help, I already outlined. Okay, so we're going to try some examples. So you can just compare the quantities together, like 300 versus 30 grams. Which one do you think would have more energy if they are in all of the same conditions? But I also want you guys to calculate what the actual energy would be so we get practice with that equation. So here we go. And I outlined it a little bit for you guys to help you with placing things in the correct spot. But please pause the video and try calculating the amount of energy, or Q, for each of these substances. When you're ready for the answer, press play. All right, so let's see how you guys did. So what we were doing in the first one was comparing the same substance with the same temperature change, but different mass. Actually 10 times the amount of mass. In the second one, we are comparing the same amount of mass, again, the same temperature change, but we are looking at different substances. And if we look at the specific heats, it looks like the specific heat of iron is almost double to that of silver. All right, so how I would have set this up is like this. And the calculations are pretty straightforward, even though there are a lot of units present. Just plug mass in for M, specific heat in for C, and your change in temperature in for delta T. So how you would type this first one into the calculator is 30 times 4.18 times 80. All right, and here are the quantities that you guys get for each of these. So for the first one, you can see that if you have 10 times the amount of mass, you have 10 times the amount of energy. And the second one, if you have double the amount of specific heat, you have double the amount of energy. So substances that have very high specific heats, or double, triple, quadruple the amount of specific heat than something else, it takes double, quadruple the amount of energy to increase that substance 1 degree Celsius. All right, now, I hope you guys remember this table from the last lecture, but we're going to look at the positive and negative values for heat and how that is possible. And it all refers to the direction that the temperature is changing. So if the temperature changes from low to high, you have an endothermic reaction, or an endothermic change. It does not have to be a reaction. And an endothermic change means that heat is entering the system. If the temperature changes from high to low, you have an exothermic reaction or an exothermic change. Again, does not have to be a reaction. And heat is exiting the system. And when it's exothermic and when heat is exiting, your Q, or your heat, is negative because it is leaving. And I know you guys remember the heating curve from Physical Science A. Now let's add in the endothermic and exothermic sides. So if we are going up or increasing our temperature, heat is entering the system, endothermic, positive Q, positive heat, leaving the system, going the other direction from high to low, exothermic, heat exiting the system, negative Q because it is losing or giving off heat. All right, now we're going to dive into some more calculations. So again, use the equation, the Q equals mc delta T. And for this one, it's pretty straightforward. Plug in the M. You do need to have the specific heat of water, so we'll be using that 4.18 joules per gram degree Celsius again, and determine your change in temperature. All right, pause the video, try this one out. When you're ready for the answer, press play. All right, let's see how you guys did. Okay, so I have all of my variables outlined up at the top left. And when you plug it in, it's pretty straightforward. When you punch it into a calculator, 500 times 4.18 times 10. And I outlined how the units are canceling out so that we actually end in joules. So when you multiply the mass times specific heat, that is how the grams cancel out. When you multiply the temperature by specific heat, that's how Celsius cancels out, and you're left with joules. So it's also very important if you guys are ever given a temperature in Fahrenheit or if you're given a temperature in Kelvin. If your specific heat has units in degrees Celsius, you will need to perform a conversion to get your units into Celsius so that they actually cancel out. And the same thing applies for mass, which I'll talk more on the next slide. If you guys want to look at this a little bit longer, press pause. I'm going to go on to the next slide now. All right, next example. Why don't you guys read this one and try calculating the amount of energy it takes to change the substance from 125 to 75 degrees Celsius. All right, let's see how you guys did. Okay, so this one, you first needed to perform a mass conversion. So kilograms into grams, really simple. All you do is move the decimal place over 3 spots to the right. So 0.25 grams is 0.25 kilograms is 250 grams. And you would not be able to plug in the 0.25 kilograms into the equation, only if you wanted to end in kilojoules. Okay. All right, so after we determine the amount of energy, which is negative 5,625 joules, the reason why it's negative is because heat is leaving the system, and we would know that based on what was stated in the problem, how it says that iron is cooling. So if our temperature is decreasing, that means that our heat is negative because it is leaving. And the second part of the question, how much heat is gained by the water? Well, if the iron is in the water and the iron has lost that amount of heat, then the amount of heat gained by the water is 5,625 joules. But it would be positive since it was gained. All right, thank you guys for watching. Please go check Google Classroom for your assignment for today.